Good afternoon, ladies and gentlemen, and welcome to the Hydrogen Fuel Cells and Batteries Group Exhibit 2018. You're here with me today at the Technical Forum. I invite all of you who are here to please take a seat, enjoy a coffee, water, or juice while we listen to our next presentation. Our next talk will be on hydrogen in a sustainable energy system, a combination of storage medium and fuel. And here today to talk with us is the Deputy Chairman of DWV, Dr. Johannes Töpler.
Okay. Thank you very much for the kind introduction. And the question, hydrogen in a sustainable energy system, combination of storage medium and fuel, is not a detail but a strategic question. And I would like to present you the ideas of the German Hydrogen and Fuel Cell Association on this topic. And if we look for the energy supply, we will have actually our energy supply is dominated by oil, gas, natural gas and coal. And in future we will have more and more wind, photovoltaics, solar thermal energy, biomass, geothermal energy, and so on. And the most important difference between the different energies, the fuel energy, the conventional energies and the new ones, is that in the past the energy was concentrated in matter, in oil, coal, gas, and from this fuel-based energy system we had to produce electricity. In future we will have, for example, wind power, photovoltaics, solar thermal energy, and from this the first step to energy which can be used for technical purposes is electricity. That means we will have a strategic transition from fuel-based energy system to an electricity-based energy system. That's a very important strategic step, and now we have to look how the electric energy from these sources will be available. And here you find an example for the power distribution in the E.ON grid in 10 days in 2007 in March, and you see here the power distribution in the electrical grid from wind energy. And in Germany we have the legislative situation that this power should be multiplied by a factor of 3 till 2020, and we have reached this power distribution right now a little bit earlier, and you see here the distribution about in these 10 days with actual power exploitation. And the vertical load in the network was the brown line, that was this one. And you see here that in these days the supply could not be satisfied by the demand by far. There is a factor of more than 5. And here are some other days, 2 days, where the supply outreaches the demand by far. And this means that we have to store the additional energy of these days to have it available, for example, in days when we have not enough wind energy. This fact is well known, but you have to look on the scale. We have here round about 5,000 megawatts, that means 5 gigawatt, and here in between this gap is round about 10 to 12 gigawatt. And 10 to 12 gigawatt for 4 days, for example, 100 hours, is 1 terawatt hour. That means for situations which can be described, for example, in this manner, we have to store round about 1 terawatt hour. It's a very, very big energy amount. For example, if you pay for 1 kilowatt hour 30 cents, then we discuss with 1 terawatt hour about 300 million euros. And one example to do this, I will show you that this amount of energy can be stored in hydrogen. The first example of a closed cycle energy supply is shown here. We have from wind energy, electricity. Photovoltaics is also possible. We have electricity, and this can be distributed directly. And we can supply the electricity directly to battery-driven electric vehicles. If we have more electricity available that can be used directly, we can produce via electrolysis hydrogen. How it works, you have seen in the last contribution. And this hydrogen can be delivered directly to fuel stations for electric-driven vehicles driven by hydrogen with fuel cells. And it can be stored in very, very big caverns. And from here, even the fuel station can be delivered, or via gas networks, households and industry can be supplied with hydrogen as energy carrier. And this hydrogen can again be re-electrified for the electric grid by fuel cells or even by turbines. And now, once again, the size of storage system. We have in Germany some pump storage systems, and we need it very urgently for the stabilization of the 50 Hertz frequency of the network. And in this case, we have round about 1 gigawatt in general and 5 gigawatt hours for energy. We have adiabatic compressed air systems with an energy content of round about 23 gigawatt hours and round about 2 gigawatt electric power. But for hydrogen, we need round about terawatt hours to compensate energy gaps of round about 4 days with up to 10 gigawatt hours. And this storage system, or this amount for stored energy, can only be supplied by hydrogen. The reason is, in hydrogen we store chemical energy, or the energy of a chemical reaction. We have 380 gigawatt hours per cubic meter in hydrogen compressed with round about 120 bars. And this is a net hydrogen storage. And if we subtract the energy loss for electrolysis and fuel cells for re-electrification, we have around about 170 kilowatt hours per cubic meter. In comparison to pumped hydro systems, it's 0.7 kilowatt hours per cubic meter, or for adiabatic compressed air systems, 2.4. The reason is, here we have potential energy, here we have chemical energy, but this chemical energy must be reversible. And with hydrogen we can do it. We can combust hydrogen with fuel cells, and we can re-electrify it by electrolysis. We have the possibility to store reversibly chemical energy. The consequence is, hydrogen makes renewable primaries energy ready for power supply, and it makes the energy transition affordable by storage capability of big systems. On the other hand, we can use fuel cells for mobility, for example in motor cars, buses, trucks and so on. You see several cars, for example from Daimler, at the booth of NOW. The transportation system are the storage tanks with compressed air. You see some samples today here on the Messe. We have an additional battery. I will tell you why, the reason a little bit later. We have here the fuel cell stack, the supply system and the electric engine. And with a car of this type, Daimler B-Class, the most impressive test has been done several years ago It was tested by a turn around the world in 175 days with 30,000 kilometers. It was related to the 125th birthday of Daimler. And the test of these cars has shown that it is possible to construct and to operate these cars under serial conditions. And the absolutely new engine of this system is shown here, and it is built in the Daimler car, the Gear GLC, which is shown here today on this fair. Other car manufacturers have other systems. For example, in the case of Honda, it's a four-wheel drive, one drive at the front axle, a wheel hub drive at the rear axle. Even this four-wheel drive system is just in operation. And one of the most impressive cars and the first in serial production was a Honda Mirai with a similar packaging. It's similar to the Daimler system, but it was the first one in a serial market penetration. And one comparison to battery-driven cars. Even fuel cell-driven cars have an additional battery. We need the battery for this. I will tell you why. But one comparison, for example, for the range of the cars. In the case of a gasoline car, you see here only the gasoline. Here is a typical chemical formula for this, is to be transported and stored within the car. Oxygen is withdrawn from air, and carbon dioxide and water vapor as a chemical combustion product are released to air as well. In the case of a hydrogen car, we need the hydrogen on board of the car as stored energy, and oxygen is withdrawn from atmosphere, and hydrogen and water is released, or water vapor is released via the exhaust system. In a battery-driven vehicle, for each electron, you have stored on board the anode material and the additional cathode material, for example, with big molecules for each single electron. Here you see the summary formula. And if you want to construct the vehicle for a long distance, for example, for a doubled distance, you need a doubled diesel or a gasoline tank, you need a doubled hydrogen tank, or you need a doubled battery. That means in the case of a battery-driven car for long distances, you need a lot of battery weight. For example, in the Tesla, more than 600 kilograms. On the other hand, an additional battery is very suitable for a hydrogen-driven car, because you can make the hydrogen system smaller. For example, for peak loads, you can use the battery as energy storage for reusing the braking energy. For this case, you have here a generator instead of a motor, and the generated electricity can be stored in the battery. And the third reason is you have an additional heating system, even for preheating the non-operated car. In the case that you want to start a car in very cold weather, you can start the fuel cell producing electricity, not for driving but for filling the battery. You can get heat for preheating the car, and when you drive, you can drive with electricity from battery and fuel cell in the same way. You can use, when driving, the waste heat from fuel cell, and if you get your goal, the battery should be somehow empty, and you can refill with preheating again for the next start. That means you can heat and preheat your car without loss of range. And some years ago, 2 or 3 years ago, a lot of companies in Europe have exactly investigated which market penetration for which type of cars are more suitable for battery vehicles and for fuel cell vehicles. And the result was that in compact and medium classes with ranges up to 10-20,000 kilometers per year, that means in this triangle, battery vehicles have advantages. And in this area, bigger cars and bigger ranges, fuel cell vehicles with hybridization have advantages. In the last years, it was reported that batteries have got a lot of additional advantages. Maybe the result is that this line can be shifted a little bit in this direction, but for these cars and additionally for transporters, for delivery vans and so on, we have a lot of advantages for fuel cell vehicles. And one other point was discussed in the last years. That was the so-called methanization via Sabatier process, so that we can make from store hydrogen synthetic natural gas and to use this in cars as well. But we have to look very exactly what we do. If we have, for example, biomass, in this case we have to use combustion engines, and combustion engines have efficiencies like this. That means for high load, the efficiency is similar high as the efficiency of fuel cells. That's the efficiency of a fuel cell system. And in this case, we see that we have advantages, for example, for biodiesel cars in the range of high load. Normal passenger cars or common buses have advantages in this area. That means generally with fuel cells. The time is over, therefore let me do it very quickly. Here is a figure for methanization, where I have spoken some sentences before, and you see here when we have in this case the hydrogen line and we use the fuel cell, we have a final efficiency of the whole line from well to wheel of around about 29%. If we use the combustion engine with methanization, we have only 12. The energy loss for compressing and for methanization are nearly the same. The advantage is only in the end use of fuel cell. And if we look on the energy chain from the opposite side, and we normalize the used energy or the necessary energy at the end at the wheel, and we go back to the necessity of energy input, we see that the size of the power plants at the beginning of the whole chain is here around about a factor of 2.5 higher. That means the investment cost for producing the energy or the power equipment is higher as well. You can look for the different energy chains for yourself in the OptiResource program from Daimler. Look at the internet by Daimler and OptiResource. You can look the efficiencies and the carbon dioxide emissions directly for all steps, and you will find the emissions by energy and the emissions for carbon dioxide as well. Today, the biggest step for mobility with hydrogen is the railway. You see here the first investigations by the University of Birmingham. Now, 10 years later, we have a train which is operated in Germany. The consequence, hydrogen introduces renewable energies into mobility. It enables electric vehicles to reach long distances, and it makes mobility carbon dioxide free. And now I thank you for your attention, and maybe we see each other at our internet site.
Thank you so much, Dr. Töpler. At this point, if we have any questions, I can bring the microphone down to you. or if you think of anything at a later moment, you can find Dr. Töpler at booth C51. And will you be here for the rest of the fair?
See?
C51, yes, for DWV.
Okay, thanks.
Okay, great. Stay tuned. We have our next presentation coming right up. We'll be listening to online hydrogen quality measurements according to international standards. Thanks so much.